On May 25, 1961, President of the United States John F. Kennedy led the nation toward a new frontier, the moon. President Lyndon Johnson has continued that leadership, and more than 100,000 scientists, engineers, and technicians, under the guidance of the National Aeronautics and Space Administration, have completed the one-man flights of Project Mercury and the two-man flights of Project Gemini. Next comes Project Apollo. In the not-too-distant future, this 364-foot giant will carry 3 Americans on an historic journey into space, to the moon, and home again to Earth, achieving for the United States the operational capability for manned space exploration. The United States moon mission profile requires separation of the Saturn V first stage from the Saturn V second stage, about 38 miles above the Earth. Ignition of the 5 liquid hydrogen-fueled engines will produce more than 1 million pounds of thrust and boost the launch vehicle and its Apollo spacecraft to an altitude of about 110 miles and a velocity of over 15,000 miles per hour. Boost time for the Saturn V second stage will be approximately 6.5 minutes. North American Aviation's Saturn second stage booster consists primarily of a 266,000-gallon liquid hydrogen tank, an 81,500-gallon liquid oxygen tank, and 5 powerful engines. A design and technical advance in the state-of-the-art was achieved with the manufacture of a specially insulated common bulkhead required to separate the different temperatured liquid hydrogen and oxygen. Liquid hydrogen must be maintained at minus 423 degrees, while liquid oxygen must be kept at minus 297 degrees. Final assembly of the Saturn second stage is performed at Seal Beach, California, where explosive-formed Gore segments are joined by meridian welds to form each complete bulkhead. The common bulkhead is insulated with a layer of phenolic honeycomb core, while the forward bulkhead is covered with a layer of foam-filled insulation. Hydrogen tank cylinder walls are made of quarter panels of machined and brake-formed aluminum alloy, bonded with foam-filled insulation, then joined by vertical welds to form the tank cylinders. Stage sub-assemblies, tank wall cylinders, tank bulkheads, skirt sections, thrust structure, and engines are mated in a vertical assembly building. Containers, electrical harnesses, and systems lines are installed. After final assembly, each system is individually verified before integrated all systems tests subject the booster to simulated operational conditions before firing. A landing ship dock, modified for the shipment of large boosters, transports the booster from California through the Panama Canal to NASA's Mississippi Test Facility, where the stage is installed in a test stand for additional integrated testing of systems and hardware under static firing conditions. Full thrust of this Saturn V second stage was achieved for 6.5 minutes, the required boost time for the Apollo lunar mission. This stage has now been delivered to the Kennedy Space Center in Florida in preparation for the first Saturn V launch. Climaxing a series of Earth orbital missions, the ultimate objective of Project Apollo is to land men on the moon and assure their safe return to Earth, a mission which will achieve for the United States an operational capability for manned space exploration. At launch, The Apollo spacecraft consists of a launch escape system, a command module, a service module, and the spacecraft adapter, which houses the lunar module and attaches the spacecraft to the Saturn V launch vehicle. The launch escape system, vital to crew safety in the event of launch pad or suborbital abort, uses rocket motors, separation devices, and automatic sequencers to protect the crew if an emergency occurs. The command module houses the flight crew and equipment necessary to control and monitor all spacecraft command and service module systems. The service module houses the fuels and engine to create the thrust required for course direction and large changes in spacecraft velocity after booster separation. It also provides other vital systems to support the astronauts during the long lunar flight. Located in Downey, California, North American Aviation's Space and Information Systems Division was awarded the principal contract for the NASA Apollo spacecraft command and service modules in December 1961. Developing a spacecraft to transport and protect man in the hostile environment of space involved complete new concepts of design, of materials, of fuels, and manufacturing methods and procedures. The Apollo spacecraft would be the most sophisticated device ever flown by man, enduring temperatures ranging from minus 150 degrees to more than 5,000 degrees during re-entry. The spacecraft would have to withstand intense loads at launch, protect against radiation and meteorites during the flight through space, provide control systems that would allow man to perform the duties required by such a mission. Thousands of companies across the United States responded to a national goal. Scientists, engineers, and technicians joined forces, and Project Apollo began. New metals were forged. New weld techniques were developed. New chemical etching processes were created. New insulation materials came into being. New inspection methods were devised. A new spacecraft began a new era for science and industry. The service module required new systems, new tanks to contain hypergolic propellants, an engine to provide thrust. It was assembled, and in the largest clean room in the world, components, structures, engines, and systems merged with man. Electronic control assembly packages were subjected to environmental tests to prove stability and quality. Communications equipment was checked and evaluated. Fuel cells providing electrical power and drinking water for the astronauts were tested. Reaction control engines were fired under simulated space conditions. The main engine for the service module was proved under start, run, shutdown, and restart procedures. Crew system engineers tested crew couches with adjustable headrests, seat pans, leg rests, and restraint harnesses. In-flight tool sets were evaluated. Mirrors for increased interior and exterior vision were made. Alignment sights to aid orientation during in-space docking maneuvers were tested. The launch escape system was qualified in a series of tests, the final under the worst possible conditions. The system performed successfully. The Earth landing system using 3 main parachutes was man-rated. Water impact and flotation tests were made to provide structural support data for manned flights. The spacecraft withstood extensive testing at different angles of impact. A specially equipped Air Force jet cargo plane flew high parabola missions which allowed astronauts to train for the weightless conditions of space during brief periods of zero gravity. Space suits were evaluated. Sleep conditions were studied. A fixed base mission simulator was produced, and astronauts began to train in system operations, space navigation, and mission procedures. Apollo systems and subsystems were tested individually prior to installation in the spacecraft. Then, after completion, the spacecraft was tested with all systems integrated and programmed with simulated mission events in a dress rehearsal for flight. Carefully packaged for shipment, the spacecraft was then transported by air from California to the Kennedy Space Center in Florida. In 1966, the first mating and rollout of the Apollo Saturn V configuration was performed by NASA at the Kennedy Space Center. Facility checkout hardware of the Apollo spacecraft, the spacecraft adapter, the Saturn third stage, the Saturn second stage, and the Saturn first stage were stacked for test. Towering 364 feet into the Florida sky and weighing more than 6 million pounds, the Apollo Saturn V configuration's 3-mile trip to the launch pad confirmed operational procedures vital to lunar mission launches in the future. In 1966, unmanned Apollo flights began on the uprated Saturn I vehicle. These missions demonstrated the compatibility and structural performance of the spacecraft and boost vehicles, determined the thermal performance of the command module heat shield and ablators during re-entry, proved the command module was qualified for manned entry from low Earth orbit, and provided data from onboard subsystems for future manned flights. These missions were successful. North American Aviation's Space and Information Systems Division, under contract to NASA, is delivering more Apollo hardware. Astronauts are training. Soon, man will enter space in a new spacecraft as the Apollo program poises on the threshold of manned space exploration.